Good afternoon. Pichanto, Sawatara, Panyawat, Senlong, and others. I can see only a few names on the screen. Guys, you can hear me well, I hope. Right, Panyawat? Can you hear me?
Yes, sir.
Good. Very good. Okay, then, guys, I hope you're all doing well. So let's continue. And we have only 1 hour class today. That's one session. And tomorrow we will discuss everything that we have studied so far. Okay. And also we may have some kind of discussion. And as I told you, next week we will talk about Newton's method and antiderivatives. Actually, these are not too much things, but especially, again, I suggest you to spend a bit more time on 4.3, 4.4, and 4.5. Okay, these are, let's say, the most important concepts in this chapter. So yesterday, we talked about monotonic functions and the first derivative test. This monotonic means that, okay, the function where is always increasing or always decreasing over a certain interval. Such functions are called monotonic functions. And also actually the first derivative test, right? And this is important to determine the, what is it, intervals where the function is increasing and where it is decreasing. So we need to find the intervals of this increasing and decreasing part of the function. And after that, we talk about concavity and curve sketching, right? On over which intervals the function's graph is concave up or concave down. Okay. To do this one again, actually, we need to use the second derivative of the function because the intervals where the second derivative of the function is positive, there the function's graph is concave up, right? And it is negative, it is concave down. And also, actually, we were introduced with one new concept that is, what is it? Point of inflection. The point of inflection is a point where the concavity of the graph of the function changes, right? Maybe from concave up to concave down, or from concave down to concave up. Anyway, we did a few examples. As you practice a few more questions, you'll gain deeper intuition about these concepts. So today, guys, we are going to make use of these two things. That is 4.3 and 4.5 to solve problems in our applications. Okay, applications means that they are used in different branches of what is this, science, maybe in chemistry or economics, right, or physics or pure math or geometry. Okay. So again, it's a long thing. You don't have to read everything, but in general, right, when we are solving or dealing with word problems in math, the most important step is reading the problem well. Read means that just not read the problem. And how should we read this? We should just scan. Scan means read it quickly. You don't have to understand every word in the problem. Okay. And at this, when you just read quickly, at this, you have some kind of, what is it? Idea, general idea about the problem, right? And after that, the second time, you should read a little bit slower. And if you're reading on a paper, even actually on a tablet, right? And we have a highlighter, we can highlight the key words. I mean, the most important words for this problem. And if it is related to, for example, I don't know, in physics or geometry, and also it is suggested to draw a picture, okay? And also it helps you to understand or visualize this problem. And after drawing a picture, we need to label, it is called a size, right? And introduce variables to denote unknowns. And after that, the most important part is you need to set up an equation that relates the unknowns, right? That is actually the most challenging part. And after that, we need to solve this and get the answer, okay? So again, these optimization problems, the best thing is you have to practice a bit more problems. For every student, I would suggest at least to solve, let's say, 12 questions from this exercise. I mean, just yourself, like, sit and choose, for example, let's say question 1, 5, 10, 15, 20, 25, 30, 35, 40. Practice these questions and you will gain some idea about this concept, okay? So we have participants. Okay, I have just muted all of you, but if you have any questions anytime, you can ask. Guys, let's start with this example. in this question, an open top box is to be made by cutting small congruent squares from the corners of a 30 centimeter by 30 centimeter sheet of tin and bending up the sides. How large should the squares cut from the corners be to make the box hold as much as possible? So what does it mean? It means that you are given a rectangle, but here this 30 by 30 is just a square, right? A sheet of tin. So you are going to make some kind of container. How do you make a container? So we need to cut some corners, right? And after that, if you just fold them, right? If you just fold them, you will get a container that is on the right-hand side. And since also we're expecting that, or we want our container to hold as much as possible, which means that it is volume must be the greatest, right? The maximum. So after drawing this picture, actually I just put this, even this picture is not given, we need to draw this picture, right? The tin of tin, or a shade of tin, and after that label it is size. So number one, since the question is how large should the squares cut from the corners be to make the box hold as much as possible. We don't know the length of the square. Suppose that the side length of the square is x, and also that's x, right? So at the time, if you just fold this, actually the height of this container, it will be x. And since it is length is 30, and also this one is x, right? The remaining part will be 30 minus 2x. And the same thing because it's symmetric, right? And also this will be 30 minus 2x. It's 30 minus 2x, 30 minus 2x, and the height. So to find the volume, what is the volume of, what is it? It is a container like a cuboid, right? Is equal to length times width times height. And it is length is equal to 30 minus 2x. And also it is width is 30 minus 2x. That's why I just multiply this by, by itself, which is squared. And after that, we need to multiply by its height. So its height is x, okay? And if you want, you can just write it as, what is it? Expand this and write it in a bit different form. So here we have v is equal to 2. It's the common factor, right? 2 squared is equal to 4. So I can write it here as 4. And what is it? Here we have x squared. So here we have x cubed minus, here we have 15. 2 times 15 is 30. So minus 30x squared, and plus 15 squared is 225. So here we have 225 x. I just wrote this inside because it's easy to differentiate this. So that is our volume function, right? So we are expecting this volume to be the greatest. To do this one, first we need to find actually maximum value of this function, right? And where, on which interval? Our interval is, since actually the length is, what is it? 30, our x, right? It must be between 0 and 30, because it cannot be greater than this. Of course, it cannot be equal to 0, otherwise, what is it? It will be just the whole container. I mean, the sheet of tin, we cannot make a container from this. So that is the interval or domain of this function, right? So that's the first step. And now the second step is to find its maximum value, right? So how do you do this? We need to find its critical points. So if you differentiate this with respect to x, that's equal to 4, is just constant number. Here we have 3x squared minus 60x plus 2 to 5, right? And to find the critical point, this should be equal to 0. And all of these numbers are divisible by 3. So if you just divide both sides by 12, so here we have x squared minus 6 is divided by 3, it is 20x. And 225 is divided by 3, it is 75. That's equal to 0. What is this? Just a quadratic function. And first, I should try must be factorization method, which is fast and easy, right? Am I recording? Okay, good. So the 75, I can just write it as minus 15 times minus 5, right? And then minus 15 plus minus 5 equals minus 20. And that's why I can factorize it as x minus 5 and x minus 15, that's equal to 0. Okay. So because minus 5 minus 15 is equal to 75, minus 5x minus 15, 5x, 15x, that's equal to minus 20x. Now from here, x is equal to 5 or x is equal to 15. So these are the critical points, right? So the second step is now we need to find which one gives us maximum or minimum, okay? And also, if you notice here, this x equals 15, at the time this 15, 15, it will be just line, it will be 0, right? So it's also not possible. Of course, I can just actually, what is it? This x, I think this x, it must change between 0 and 15. It cannot be 30 here, right? So now actually this, when x equals 5, it gives us maximum value. But of course, I need to verify this. How do I know that? In our next step, right? And using the second derivative test, if you differentiate volume one more time, and here we have this 12, right? Here we have 12. Inside here we have x squared minus 20x plus 75. That's equal to 2x and then minus 20, or which is equal to 24 and x minus 10, right? So now at this value at 5, right? V double prime of 5, that's equal to 24 times 5 minus 10, that is negative 5, which is less than 0, right? Less than 0 means, if you remember the second derivative test, if v prime of 5 is equal to 0 and v double prime is negative, that means that actually at this point, the function graph is concave down, right? So at this point, the function has local maximum. So what is the question here? How large should the squares cut from the corners be to make the box hold as much as possible? Dot, dot, dot. The length of the square must be 5 centimeters. If you're given 30 by 30 sheet of tin, okay, if you just cut 5 centimeter, squares whose side length is 5 centimeters from 4 corners of the tin, the sheet of tin, and make a container, it will hold the maximum, volume. Or different numbers, you can check this. However, when it is 4 or 2 or 5 or 7, you will see that they will hold less than this. That is one real life application of derivative, how to find the optimum solution, the best solution to the problem. Okay, guys, the second problem. You have been asked to design a 1-liter can shaped like a white circular cylinder. What dimensions will use the least material? That is another problem from our daily life situations, is asking that we are going to design, or we are asked to design a 1-liter container, which is in the shape of, cylinder, right? There's a cylinder. And the cylinder, we have two important dimensions here. Number one is, it is radius, right? It is radius, and it is height, is h. And you have been asked to design a 1-liter can shaped like a red cylinder. And it says that the volume must be 1 liter. Okay, so what is 1 liter? 1 liter is equal to 1000 cm cube. Okay, let's say we are measuring everything in centimeter. So, and what is the volume? Volume is pi r squared, base area, times height, right? So this should be equal to 1000. All right. The question is, if we are going to design such, cylindrical, let's say, can, okay, and if you're going to use the least amount of material to make this one, what must be the dimensions of this cylindrical tank or something? Okay, that means that, that is dimensions that r and h, we have to find the year values. Okay, So to find what is this cylindrical tank, is it open or not? It's not. Okay, if we just open this, for example, if we just cut through this line and unfold with this, right? So when you open this, we will have this kind of material that or we're going to use, right? Maybe so big, but here we are given a top, right? And this one is in the bottom, and this one is the top. Okay, so what is the length of this rectangle? It is 2 pi r, and it is height is h, and the radius of this circle is r, so it is area is pi r squared, right? So that is the first one. The second one is the total surface area will be equal to, what is it? 2 pi r squared, top and bottom, plus, and here this curved area that's equal to 2 pi r times h, or simply that's equal to 2 pi r, and here we have r plus h. Okay, so this one is radius. So now we want to minimize this, right? To minimize this, what must be the dimensions of radius and the height? Okay, radius and the height. Now from the first equation, I can make connection between h and r. So which one is easier? Should I express actually h in terms of r or r in terms of h? But you see here, if I express h in terms of r, maybe it will be, because only we have one h here. So from here, what is h? H is equal to 1000 over pi r squared. So now this s becomes a function of r, right? S of r will be equal to 2 pi r squared plus 2 pi r times, what is h? That is 1000 over pi r squared. And pi, they cancel each other. Also r cancel each other. That's equal to 2 pi r squared plus pi cancel each other, r cancel each other. So here we have 2000 over only r. So that is the surface area. So now to minimize this, first we have to find it is, what is it? Critical point. So if you differentiate s with respect to r, or just to make this more clearly, let me just write here ds and the dr. The derivative as respect to r, that's equal to, differentiate the first part, that is 4 pi r, minus, because here we have r in the denominator, that's equal to, minus 1 comes to the front, so that's equal to minus 2000 over r squared, right? And to find the critical point, this must be equal to 0. Okay, so again, not the else, let me just write here, since it is clear from this context as prime. So now for me, if you solve this for r, what do we have here? 4 pi r is equal to 2000 over r squared, right? And just take this r squared to the left, 4 pi to the right. So from here, we will get that r is equal to 4, 2000, they cancel each other. So that's equal to 500 over, what is it? Here we have pi. And on the left-hand side, we have r cubed, right? Take cube roots of both sides. So here we have cubic root of 500 over pi, okay? So that is actually if it has global maximum or minimum over the given interval. At this point, it must give us maximum or minimum. But how do I know that actually when r equals this number, cube root of 500 over pi, it gives us minimum or maximum value of s? To actually answer this question, again, now we need to use the second derivative test. So the third one, if you differentiate one more time, and if you differentiate this is equal to 4 pi, right? And this minus comes to the front, again, it becomes plus. So here we have 2, right? That's equal to 4000 over r cubed. Now from here, what is r? Actually, if you evaluate this at this point, as see here, it's a positive number. So this s double prime at this value, cube root of 500 over pi, right? And because it is 4 pi plus 4000 over positive number, that is positive. So that means that at this point, the function's graph actually is concave up. That's why here it gives us local minimum. So that's why when r is equal to this and h is equal to that number, right? It gives us actually, we will use the least amount of material. So now if you evaluate this with the calculator and dots, 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 then the dimensions must be, let me just write here, r is equal to cube root of 500 over pi. And unfortunately, I don't have calculator right now. You can calculate yourself. So here we have h is equal to 1000 over pi times this r. Okay, what is r? Let me just write here r0. And also here we have r0. Whatever you have here, substitute and evaluate this. It gives us the dimensions of this cylindrical tank or tin or whatever it is. That is another problem, or is it about applied optimization or optimization problem? And we are just finding optimal solution, the best solution, right, to make to design this 1 liter can shaped like a right circular cylinder. Okay, another question. A rectangle is to be inscribed in a semicircle of radius 2. What is the largest area the rectangle can have, and what are its dimensions? Okay, so it says that we are given kind of semi, what is it? Circle, right? Semicircle. And here we have semicircle. And suppose this is a semicircle. And we are going to draw the rectangle, which has the maximum area. So let's say our rectangle is something like this. Okay, suppose that is our rectangle, okay, drawn inside the semicircle. Okay, now we need to find the dimensions of this rectangle. Now to do this one, okay, what is it? It says the radius of the circle is 2, okay, and suppose that this length, all right, this length is equal to, let's say it is x, that means it is x over 2, right, and this remaining part will be 2 minus x over 2, and also this part will be 2 minus x over 2, because if you just add them together, it's equal to 4, right? And and how about actually the width of the rectangle? I don't know. Let's say this width is, let me just label this by y. Okay. At the time, the area of the rectangle will be x times y. So now since we are looking for the maximum area, right? So we have two variables. How can I reduce these two variables into one variable? So I need to eliminate one of them from the equations. At the time, a becomes only a function of a single variable. Okay. To do this one, I'm just going to use Pythagorean Theorem. So if you just connect actually the center of the circle with this, and also it's a radius, right? The radius is given, that's equal to 2. And how about the length of this part? That's equal to x over 2. And how about height? It is y. And using Pythagorean Theorem for this right angle triangle, here we have y squared plus h over 2 squared. That's equal to 4. Right? Now from here, either I can express y in terms of x or x in terms of y. So let's just use x here. So y will be equal to square root of 4 minus x squared over 4, right? Or which is equal to square root of 16 minus x squared and over square root of 4, that's equal to 2. So this is how x and y are related to each other. Okay, so that's our first step. Let me just write here, this is our first step. So now from here, I can just find a in terms of x. What is x then? It's equal to 1 over 2 times x times 16 minus x squared. Now a becomes a function of x, because if I know x, also we can find y. Okay, and since we are looking for the value of x, where a is maximum, a is the area of the rectangle, and it's a function of x, it's a continuous function, right? So to do this one again, we have to go through those steps. Number one is, just to save some space, let me divide in two parts here. So what is a prime? If you differentiate a with respect to x, so that's equal to 1 over 2 times 16 minus x squared, right? And plus, here we have 1 over 2 times x. Now we have to differentiate this. So that's equal to 1 over 2 times, differentiate inside this, that's equal to minus 2x. Unfortunately, I need to cross this, and times 16 minus x squared, 1 over 2 minus 1 over 2. So that's equal to 16 minus x squared to the power of minus 1 over 2. Okay. So now, if you simplify this, what do we get here? Equals, again, 16 minus x squared over 2. And this 2 to cancel each other. Here we have minus, and here we have x squared, right? So here we have x squared over 2 times square root of 16 minus x squared. Okay. So, or even if I simplify this, I think I can get this. The common denominator is 2 times 16 minus x squared. And the 16 minus x squared minus x squared. So that's equal to 16 minus 2x squared. Anyway, I think these two to cancel each other. I can write here 8, right? And minus x squared. That is 8 minus x squared over square root of 16 minus x squared. Okay. So now if you find the critical points, right? Where are the critical points where actually the derivative of the function is 0 or it's not defined? But actually when it is not defined, denominator must be equal to 0. Where? When x equals plus minus 4. But what is the domain of this function? From here, domain of the function is, what is it here? X actually belongs to, it cannot be greater than 4. So it is between 0 and 4, right? Maximum it can be 4, even it cannot be 4. So since it cannot be 4, we are just excluding this 4, because 4 is not in the domain of this function. So from here, the critical points are x equals plus minus actually 2 square root of 2, and also x is positive here, right? It's a length. So I'm just excluding this. The only possible answer, I mean the critical point is, it is 2 square root of 2. Okay. So now guys, if you differentiate this one more time and evaluate this at this value, you will see that the second derivative is greater than less than 0. Because if you evaluate this f double prime of 2 square root of 2, we can just evaluate this. You will see that it will be less than 0. So which means that actually this a 2 square root of 2 will be maximum value or doable maximum of this function. Okay, and since x is equal to 2 square root of 2, now if you substitute there, we can find y. So dot, 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 let me just write here, x must be equal to 2 square root of 2. And how about y? If you substitute here, it is 8. 16 minus 8 is, it is 8. And square root of 8 over 2, that's equal to square root of 2. These are the dimensions of this rectangle, so that it will have the maximum area. So what are the dimensions and what is the largest area? Largest area and maximum will be 2 times square root of 2 times square root of 2, which is equal to 4. The maximum possible area will be 4 when its length is 2.2 times square root of 2 and its width is square root of 2. Okay. All right. Guys, I will solve one more question, okay? And after that, the rest of the questions, we will discuss them or solve them in the classroom. Example 6, find the volume of the largest right circular cone that can be inscribed in a sphere of radius 3. Okay, so find the volume of the largest right circular cone. So it says to find the volume of the largest right circular cone that can be inscribed in a sphere of radius 3. So we are given a sphere and whose radius is 3, and we are going to make, actually, what is it? And you can just imagine that you are given kind of wooden piece, okay? And we're just cut out, what is this? Cone from this wooden piece. We want our cone have the largest volume. At the time, what must be the dimensions of this cone? Okay, so now suppose that this is the top. Okay, we have just drawn this one. Okay, this is the base of the cone sitting inside this sphere. Okay, suppose that its radius is x. Now, if you just connect the vertex of the cone with its base, right, and this line segment, since it is passing through the center of this sphere, and this top part, it must be 3. And the remaining part, let's say it is y. So then it says, since volume, what is the volume of this cone? Volume is equal to 1/3 times pi times r squared. So our r is x squared times height. Now, what is the height? Height is y plus 3. So that is the volume of the cone, right? And we want this volume to be the maximum. So for this, we need to find the value of x and y. So from this equation, to answer this question, either I need to express y in terms of x or x in terms of y. So how can I do that? Again, as see here, if I just join the center of the sphere, this is the center of the sphere with any point on the sphere here, let's say this P, and they form a right angle triangle. From this right angle triangle, using Pythagorean theorem, here we have x squared plus y squared is equal to 3 squared, that is 9. Okay, and since I see here, if I express what is it, y in terms of x, then we will have root. But instead, since we have x squared, let me express x squared in terms of y. So from here, we will get that x squared is equal to 9 minus y squared. So now if you substitute there, then our volume will be a function of y, which is equal to pi over 3 times, what is x squared? It is 9 minus y squared. And here we have y plus 3. Or if you just expand this, here we have pi over 3 and minus y squared times y, it is y cubed. 9 times 3, it is 27. And 9 times y, it is plus 9y, right? And 3 times y squared minus 3y squared minus y squared times y, it is minus y cubed. Okay, so that is our volume function. Now to find it is maximum or something, first we're going to use the first and second derivative test, right? So that's our first step. In our second step, let me just write different color here. What is the derivative of v with respect to r? So that is pi over 3 times 27, that's equal to 0, 9y. If we have 9 minus 3y squared, that is minus 6y plus y cubed. It's not plus, it is minus 3y squared. Again, 3 is a common factor. We can just factor out the 3. Then we'll have here pi times 3 minus 2y minus y squared. Okay. So now, when is equal to 0? Let's find its critical points. So that to find the critical points, this expression must be equal to 0. And since it is 0, it's equivalent to solve this equation y squared plus 2y minus 3. That is equal to 0. And if you factorize this 3 minus 1, right? 3 plus minus 1 is equal to 2. So we can factorize this y minus 1 and y plus 3. That's equal to 0. From here, y is equal to 1 or y is equal to negative 3. Minus 3 And since -3 is not in the domain of this function because it must be positive, right? It's from 0 to 6. And that's why this answer, we don't need this. It's just rejected. We don't need this answer. So the third part, and since it is 4, now I need to verify that this gives us maximum value, right? To do this one, if you differentiate one more time, v double prime, that's equal to pi and minus 2y, right? And now if you evaluate its value at 1, here at 1, that's equal to pi times minus 2, which is equal to minus 4 pi. And minus 4 pi is less than 0. Minus 4 pi is, just here, minus 4 pi is less than 0, which means that at this point, right, the function's graph is concave down. So here it has local maximum. That's it. So now we can just write our final answer, dot, 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 for the volume of the cone to be maximum. And this y, it must be equal to 1. If y is equal to 1, x should be equal to square root of 8, right? And it says that find the volume of the largest right circular cone. We need to find actually the volume. Let me just write this next to it. And x must be equal to square root of 8. At that time, maximum volume of the cone will be 1 over 3 times actually pi over 3 times x squared. X squared is equal to 8 times y plus 3 is equal to 4, which is equal to 32 pi over 3. That is the maximum possible value of the cone, which can be inscribed inside the sphere of radius 3. Guys, that's all for today, okay? Because having long online class, I don't think it's efficient. And tomorrow we will continue in the classroom and with discussions, okay? Have a good day. I will see you tomorrow. Thank you. Bye-bye.
Bye, sir.
Bye, sir. See you.
See you.
Goodbye, sir.
Goodbye.